we are having 2 hours slot to conduct our lecture, but due to some emergency work at our institute level, I am taking only 1 hour. If possible, tomorrow morning I am going to take one more lecture. Whatever today we have missed, that lecture tomorrow or day after tomorrow, one lecture definitely I am going to take. So in last lecture we have discussed about the energy reservoirs. Okay, then two energy reservoirs. We know that there are two types of energy reservoirs. One is source, which is always at high temperature, and another is sink, which is at low temperature. So these thermal reservoirs we have defined, okay, source and sink. Then we have whatever the basics required for the second law of thermodynamics, that is heat engine we have defined. So heat engine, we know that the output of the heat engine is work, and input for the heat engine is heat. So any device which takes heat as the input and doing work as the output is called as heat engine. So like that, our steam power plant, IC engine, external combustion engine, all are the heat engines. Then here we have taken one example of our steam power plant, on which our total subject syllabus is based. That heat engine we have covered. The boiler is acting as a heat source, turbine acting as a heat generating device, condenser as a sink, because here heat is rejecting, and pump, because some work we have to uh, give supply for the pump to do work, and therefore net work will be whatever the work generated by turbine, and here whatever the work generated by a turbine. Okay, so whatever the work generated by a turbine, sorry, work generated by turbine. 1 minute, I will take pointer. So WT minus WP will be the net work generated. Then afterwards we know that the efficiency formula of the heat engine, that is always here it is output divided by input. Output is WT, turbine work minus pump work. Okay, and input is heat supplied. So this is heat supplied. Okay, and this is output W, that is Q1 minus Q2. So we know that incoming is equal to outgoing. So Q1 is incoming, outgoing is W, and Q2 here, sorry, it is here, it will be Q1 minus W. So here it is considered as a Q1. So Q2 is here outgoing. Here Q1 and W are going. So we can write an equation, that is Q1 plus W. Q1 plus W is equal to Q2. Okay, and from that we got that here Q1 minus Q2 is nothing but W. Okay, or WT minus, that means WT minus WP will the network. This is a network we have to consider. Okay, if pump work we are neglecting, then WP we have to consider as a 0. Then in that case WT divided by only Q1. So Q1 minus Q2 divided by Q1, and 1 minus Q2 upon Q1. So this indicates that this is the basic efficiency formula of any heat engine. Okay, then here efficiency will not be always 100% for heat engine, because it is 1 minus Q2 upon Q1, rejected heat divided by supplied heat. Therefore this is having some quantity. So this Q2 upon Q1 is having some value. Therefore efficiency will never be 100% or 1. It is always less than 1 or 100%. But to have the maximum efficiency, we know that heat rejected should be as low as possible, and heat supplied to the heat engine should be as more as possible. Okay, then and then only efficiency will be maximum. And this q2 cannot be 0, it should be some value. We cannot make it as a 0. If it is make 0, then efficiency will become 100%. But this q2 should be some value, it should be minimum. Okay, then efficiency will be maximum. Then we have discussed about the refrigerator and heat pump. These are the devices also we want when we want to define our second law of thermodynamics, Clausius statement. So these devices we have to know. So refrigerators are there, and is the cyclic operating device which maintain the temperature of any region below lower temperature than the atmosphere. Okay, so anything temperature, anything's temperature is less than atmospheric temperature, it can be achieved with the help of only refrigerator. So these refrigerator are working on whatever the engines are working, it's reverse Carnot cycle or engine cycles. These refrigerators are working, heat pump and refrigerator. So here I have explained on that day refrigerator, it is you have here vapors are coming from the evaporator, takes the heat from the cold space, it get compressed in the compressor, its pressure and temperature will become more, then it is condensed in the condenser. Even in condenser, liquid refrigerant is converted, sorry, vapor refrigerant is converted into liquid refrigerant, and then it is throttled. But here pressure remains constant. So throttle valve, it is called as expansion valve, it decreases the pressure, and again low pressure low temperature refrigerant is supplied to the evaporator for the next cycle. Again it will take the heat from that evaporator or refrigerated space, and again it will convert that low pressure liquid refrigerant will convert into low pressure vapor refrigerant, and then compressor, it is here compressed here taken to the compressor, it get compressed and cycle repeats. And refrigerator, we know that it is working on the reverse Carnot cycle or reverse heat engine cycle. Okay, so objective are then another cycle is heat pump, again working on the same line. Okay, but refrigerator, our objective is the space which we want to maintain below atmosphere temperature. So how much heat is taken away from the refrigerator space is our objective. And heat pump, our objective will be how much amount of heat we supply to the house, so that will be acting as a here heat pump. Heat pump objective is Q1 in our diagram in our EP notation, and refrigerator space objective is Q2. How much amount of heat we are taking from the refrigerated space, and here heat pump, how much amount of heat we are supplying to the house. That way we can go for. So therefore, here we have to go for the means our air conditioning can do the purpose of refrigerator also and heating heat with the help of heat pump. Then for defining the performance of a uh, heat pump or refrigerator, we are using definition that it is a COP. We are using one term that is called as COP, coefficient of performance, and is defined as how we define benefit. What are the benefit means? Objective divided by cost means work supplied. Or here we can this definition, you forget this definition, you can remember COP of refrigerator or heat pump, it is equal to what? Here heat objective, whether heat is supplied or removed, divided by work supplied. Okay, so in this case COP of refrigerant is equal to refrigerator is equal to objective is Q2, means how much amount of it is taken removed by refrigerator or taken from the refrigerated space, that is Q2. Heat removed by the refrigerator divided by input is work is equal to W. Therefore Q2 divided by or Q here we can say that Q2 divided by Q1 minus Q2. So Q2 W means Q1 minus Q2. So with the help of this formula, one can calculate the COP of any refrigerator. Then heat pump, again here they are working on the same line, refrigerator and heat pump. Okay, so here heat pump objective is how much amount of heat is supplied to the that room, and that is nothing but heat supplied by the heat pump to the room space. Here objective is Q1, not Q2, how much we are supplying to the space. So that way divided by work supplied, so Q1 divided by W, or COP of heat pump is always equal to Q1 divided by Q1 minus Q2. Or if you rearrange mathematically, it will become 1 plus Q2 divided by Q1 minus Q2. And this relation we have to use also in the numerical. We have to remember that COP of the heat pump is equal to here 1 plus this value will become what? COP of refrigerator. So COP of heat pump is equal to 1 plus COP of refrigerator. That also I covered in the last lecture. Then I have told about the EER, that is energy efficiency ratio. For then SEER, that is seasonal here energy efficient ratio. and here these terms are required in market when we are selecting the refrigerator from the market. In this kind of here terms we have to take into consideration. So these COP of refrigerators are different for different when we want to store different food materials. Then COP of the refrigerator range of COP is going to be different for different foods that we are going to store. So for example, I will take one COP of refrigerator. When we want for ice cream units, it is 1.0 to 1.2. So again, COP for meat, dairy and produce, it will be in the range of 2.3 to 2.6. Okay. Then we have defined, after that we have defined the two important statements of second law of thermodynamics. One is second law of thermodynamics Kelvin Planck statement. How it defined? The Kelvin Planck statement is defined as, or it is stated that it is impossible to convert a cyclic operating device which will convert all amount of heat into an equivalent work. So Q in is equal to W is not possible. So W net is equal to Q in is not possible. Okay. So then some amount of heat we have to reject. Or in another language, we can say that a heat engine that violates the Kelvin Planck statement is a heat engine that violates the Kelvin Planck statement of the second law cannot be built. Means here heat engine have to always follow the statement of Kelvin Planck. Or in another word, we can say that no heat engine is have a thermal efficiency of 100% or 1. So that way we have gone for. So this diagram represent PMM1. Okay, sorry, PMM2, perpetual motion machine of second kind. Okay. Hello. I think I am taking, I am presenting screen from our college net, but I think it is disabled. So now I am presenting from, here my own device. Okay. So now I think we'll change our pattern. Now reversible, whatever is available. Now my voice is audible.
Yes, sir,
Am
Yes,
I
audible.
sir.
audible?
Voice is audible, sir,
Yes,
but
sir. Audible.
presentation is not visible.
Hello. Am I audible?
Yes, sir,
Yes,
audible.
sir.
Yes, sir.
Okay. Okay. Now we'll continue. Okay. Okay. Now reversible process will not take some. Energy reversion. Okay. We'll go directly to. Okay. So screen is visible.
Yes, sir.
Yes, sir, visible.
Yeah. Okay. Then okay. Now we'll go for Carnot cycle too. Okay. Carnot cycle is an down that Carnot cycle is an ideal cycle, and it consisting of four processes. So and two processes are isentropic processes. And this Carnot cycle is discovered by Sadiq Carnot in 1824. Is reversible processes. So that whatever the processes happening in the universe, very rare processes are reversible. Otherwise, all processes in the universe are irreversible processes. Therefore, here whatever the cycle is static, we call it cycle, not cycle. These are there are not are reversible. Okay, and reversible processes are very very few processes. Okay, and therefore these cycle become ideal, or you can say hypothetical cycle. Carnot that isentropic four processes. Out of them, two are isothermal And also isothermal processes, also very few processes are isothermal processes. Okay, and therefore here this cycle become here ideal, remain ideal. So some input given by Carnot, that a fluid, any fluid may be used to operate the Carnot cycle, which is performed in an engine cylinder, the head of which is supposed alternatively to be perfect conductor or a perfect insulator of heat. So to make that process here isentropic or isothermal, one assumption he made, that is that fluid we are going to use in a Carnot cycle be a perfect conductor or a perfect insulator of heat. Okay, then heat is caused to flow into the cylinder by the application of high temperature energy source to the cylinder head during expansion, and flow from the cylinder by the application of energy source to the head during compression. So here cylinder head is there, okay, and here this cylinder head piston is moving in the cylinder without friction. So if we have the friction in the cylinder, okay, and there is a friction in between piston and cylinder head, then that process will not be a reversible process. That will be a irreversible process. Okay, and therefore here cylinder head and piston, there should be a frictionless. There should be no friction present in between piston and the cylinder head. So these are the assumptions there. And the piston moving as perfect insulators, the cylinder head arranged the perfect heat insulator. The transfer of heat does not affect temperature of because source and cylinder maintain. Medium is perfect gas constant phase. Complex expansion are reversible. So here two processes he assumed, that compression and expansion are reversible processes. Okay, and accordingly now we are discussing the four of, so first, that is phase one. That process is called as isothermal expansion process. That we name, you name it as a process 1 to 2. So during this expansion process, the temperature T1 means, now we are considering that heat is supplied to the engine at temperature T1, and this temperature T1, okay, and at the same time we are getting the expansion. So we are having this diathermic cover is there. So it is this diathermic cover. It is acting as a outside flow of in outside will not first stage is there, or first step is there. It is 1 to 2 process isothermal expansion. And what is that? The temperature of source temperature is T1, and it takes the heat Q1 from source, and in wheels isothermally and reversibly at high temperature T1. Expansion pressure is goes on decreasing. Now second step is there. It is adiabatic expansion, or we can say it as a reversible expansion. So first is isothermal expansion, second is reversible expansion or adiabatic expansion we can say. Then the cylinder becomes a perfect insulator so that no heat flow takes place. The fluid expands adiabatically and reversibly. The temperature falls from T1 to T2. But here the process is not isothermal. Here the process is there. Here the process is of stage 1. Here process 1. The process is isothermal, but process 2, stage 2, the process is adiabatic only. Temperature falls from T1 to T2. That is called as adiabatic expansion. So we are static. Okay, so adiabatic cover is there. The purpose is again heat will not flow from outside to inside or from inside to here inside to outside. Then stage 3 is there. Now to have the cycle, so we know that when we have to come to the original position, so when we are going for a isothermal compression, isothermal expansion, adiabatic expansion, and same processes we have to carry out, so that we have to make that cycle to that point that we can state to the original state or initial state. And for that, the stage 3 is there, isothermal compression, that 3 to 4 process there. Okay, so in that case, here at temperature T2, the heat Q2 flows from the fluid, okay, and is compressed isothermally, okay, and reversibly at constant lower temperature T2. So at this is a sink, so lower temperature acting as a sink, and here sorry. So stage 3 is there, isothermal compression. Okay. So stage 3, cold energy. So at T2 temperature, the heat is taken out from this particular uh, substance, or it is rejected. At Q2 amount of heat is rejected, and it is supplied to the sink at temperature T2. And last process is there, that is 4 to 1. Okay. So it is at the bottom side. So what is that? Cylinder head becomes a perfect insulator, and the compression is continued adiabatically and reversibly, during which the temperature is raised from again T2 to T1. In adiabatic expansion, temperature is falling from T1 to T2, but in adiabatic compression, the temperature is raising from T2 to T1. Okay, so these are the four processes. Okay, now we'll go for the PV diagram and TS diagram of this cycle, the Carnot cycle. So one 1 to 2 isothermal expansion, then 2 to 3, or here we can, again heat 1 to 2, during that heat is added, okay, isothermally, okay, heat is added isothermally during this process 1 to 2. Then 2 to 3 is their adiabatic air expansion, where we are getting the work done. And here adiabatic expansion, it will follow the law PV raised to gamma is equal to constant. Then 3 to 4 process is there. It is isothermal process, and it will follow the law PV is equal to constant. Okay, and again 4 to 1, the process is what? Here adiabatic compression. So process 1 to 2, we are adding the heat. Process 1 to 2, we are adding the heat, and where 4, where to 2, where air compression. So is added in here process 1. Therefore, heat supplied to the cycle, we can call it as a Q1, okay, and is equal to whatever, because by the first law of thermodynamics, Q is integral dW. Means whatever it is supplied, same amount of heat. Therefore, this thermal expansion, and that is a work obtained that 1 2 and is given equation Q1 V1 ln of V ln of, but with PV RT. Q1 V1 is, we can call it as a MRT1. P1 is equal to RT1. Then Q1 is W12, or is equal to MRT1 ln of V by V1. Okay, so this will be M ln of V by V1. So this is considered as heat added in the. Similarly, the process Q2, where heat is rejected, okay, rejected to the sink at temperature T2. Here we can see that temperature T2 is there, but this is the temperature T1, okay, and T here it is rejected, okay. Heat rejected is nothing but required compression process. Then it requires giving the minus sign. And what is that over there? P3 V3 ln of V4 by V3. So here it is that initial condition ln of final volume divided by initial volume. So 3 to 4 process, the initial volume is V3 and final volume is V4. But here work supply therefore minus sign P3 V3 ln of V4 by V3. Work obtained by which process? Here isothermal compression process. Okay, and here we say that as PV is equal to MRT, here Q2 is equal to W34 is equal to MRT2 ln of V3 by V4, because now we are here if we change that here reciprocal here logarithm base. Okay, then in that case it will become ln of V3 by V4. Now these are the equation. One is heat supplied, now we got one, we got there the heat rejected. Now here again we can go for the TS diagram. So here process 1 to 2 is isothermal expansion where temperature is remaining constant, that is T1 is equal to T2, and here adiabatic expansion, okay, 2 to 3 process, here we are obtaining the work, okay, and 3 to 4 is again isothermal compression, that T3 is equal to T4, and 4 to 1 is there, it is considered as here it is adiabatic compression. Okay, so this is a TS diagram, this is a PV diagram. Okay, now here we got the two heat, one is heat added and one is heat rejected. Now here we know that efficiency of any cycle in current cycle is supply. In this is that to is a, it will follow the previous limit to gamma then to gamma it is equal to that it will be x and is a adaptation and PV resistance and so we know that PNR is
Sir, your
as
voice is not
equation
audible.
PNRT is equal to okay. So now it is audible.
Yes, sir.
Now
Yes, sir.
Yes, sir.
okay. Now upon P3 with T2 is equal to 1 minute. P2 upon T1. Okay, P2 V2 upon T1 is equal to 3 upon T3. Okay, then
Hello, hello.
हेलो हेलो। हेलो हेलो हेलो। अबे तो दिखा ले।
Now am I audible? Hello, am I audible?
Visible.
Yes,
Am I
sir.
audible?
Yes, sir.
Okay, now
Yes,
what
sir.
we'll
Audible,
do,
sir.
okay.
Yes, sir.
Everybody understand Carnot cycle? Carnot cycle formula of efficiency, everybody, means I was there to explain the Carnot cycle efficiency.
No, sir.
Okay, so what we'll do now, I think it is internet problem is there here in college. Okay, with me. So tomorrow morning we'll take lecture. We'll conclude the lecture. Hello.
Okay, sir. Okay.
At
Attendance,
what
sir.
You attendance. I will conclude the lecture. After giving attendance, you can quit. We'll conclude the lecture. काय उत्पास कसं होईल असलं काय अरे काय चार्ज काय करणार काय अवघड आहे.
Hello, Prince. How are you?